for section 12 is all about isomers. Now, we've already talked a little bit about isomers. Specifically, in previous sections, we've already covered geometric isomers and the two types of optical isomers, enantiomers and stereoisomers. But today we're going to kind of tie it all together and look at it in this flow chart. Now, your outline does not have all of this written in, so if you want to pause the video as I go through, you can definitely do that and write it all in. Okay, so just as a refresher, when you have molecules and they're isomers, it means they have the same molecular formula. Okay, constitutional isomers versus stereoisomers. So these are kind of the two broadest categories, and then we get into subcategories below those. Constitutional isomers, of course, have the same molecular formula because they're isomers, but their atoms differ in connectivity. In other words, the atoms are bonded to different partners, if you will. Okay, so different atoms. So here I have an example to kind of help us visualize it. If I call this carbon 1, this carbon 2, this carbon 3, this carbon 4, 1, 2, 3, 4. Okay, well, actually let me label these in terms of chemical equivalents because that's really what we should be doing. So I will call this carbon A, this will be carbon B. This carbon right here is chemically equivalent to carbon B. It's in the same environment, and so it is also a carbon B. It can be labeled carbon B as well, and then this last methyl group is identical to carbon A, so it can be labeled carbon A. So here, for the bottom molecule, this would be carbon A, this would be B, A, and A, okay? But by looking at these two molecules, we can see that they have the same number of carbons, they have the same number of hydrogens. The only difference is which atoms are bonded to which other atoms. They differ in connectivity. It's kind of as if this methyl group right here was taken off and bonded over to this carbon. That's kind of the transition from the top molecule to the bottom molecule. Okay? So, constitutional isomers, they relate to each other by having different connectivity. Now, stereoisomers, on the other hand, they actually have the same connectivity. The only thing that differs between the isomers is their arrangement of their groups in space. Okay? So, a carbon is still bonded to the same carbon as it was in its isomer, only maybe instead of going behind the page, it's coming in front of the page, or vice versa, okay? So they have groups that have the same connectivity, but differ in arrangements in space. Okay, so there are then two subcategories of stereoisomers: conformational isomers and configurational isomers. And the biggest difference between these is that, well, the difference between them is that conformational isomers can be converted to each other just by the rotation around a sigma bond, whereas configurational isomers, unlike conformational isomers, cannot be converted into the other isomer just by rotating around a sigma bond. So in other words, let's look here in green, the conformational isomers. Here is an example. We have this butane molecule, and here we have another butane molecule. The only difference is if we rotate around this sigma bond, we will turn into this bottom isomer. So really they're the same molecule. The only difference between them is the rotation about that sigma bond. And because of that different rotation around that sigma bond, it will put the different groups in different spatial arrangements depending on that rotation. Okay? Configurational isomers, on the other hand, they're stuck. Okay, there is no rotation for one reason or another. and so the spatial arrangement is stuck. So let me show you the two types. Okay, there's geometric isomers and then there's optical isomers. Both of these types are configurational isomers. Now the difference is, for geometric isomers, the reason why you can't interconvert between geometric isomers is because you have a rigid bond. Okay, either you have a ring structure, so you can't rotate around single bonds because they're part of a ring, or you have a double bond, in which case you can't rotate because of the pi bond that you have. Sometimes geometric isomers are called Sis Trans Isomers as well. And here's an example of a Sis Trans Isomer, specifically the double bond, okay, where we have a cis version and a trans version. Now, optical isomers, and there's enantiomers and distereomers, their arrangement of their groups differ in space, but it's because they exist at a chiral carbon. Not necessarily, it doesn't matter if you can rotate around all the single bonds you want. It doesn't matter because they're all bonded to that central point, which is a carbon, okay, a chiral carbon. So enantiomers are non-superimposable mirror images of each other. And here in purple I have drawn an example. Now distereomers, which I didn't draw an example, but I'm sure we'll see some down in our practice problems, they are non-superimposable and non-identical. And we did have a previous video over this. It's really kind of the catch between, well, we can't call these identical because they're not identical all the way through with all of their chiral centers, but we can't call these enantiomers because they don't have a mirror relationship at every chiral carbon either. And the one thing that you want to really remember about distereomers as well is the fact that you need at least 2 chiral centers even to be distereomers, even to have that as a possibility, okay? So really, the thing about these definitions is you just have to memorize them. Okay, so practice will help making flashcards, but at the end of the day, you're just going to have to memorize these terms and their definitions. So assuming that you've already reviewed them, right, and you feel a little bit comfortable, let's test our knowledge on these definitions. What is the relationship between each of the following pairs of molecules? Put the appropriate letter in each box. So we have quite a few options. Constitutional isomers, geometric isomers. Now remember, geometric isomers are a type of configurational isomer. Right? Remember, geometric is a type of configurational. Okay? Conformational isomers, optical isomers, which is also another type of configurational isomer. Are the molecules identical, or are they not even isomers at all? Okay. So, starting with this, the first thing that I notice here is that this OH versus this OH. Everything else seems to be the same. The only difference is this alcohol hydroxy group here is bonded to this carbon, whereas here the hydroxy group is bonded 1 carbon over. In other words, they're bonded to different atoms. Okay, the hydroxy group is bonded to a different atom. So what that tells me is that we have different connectivity which means we are going to be looking at constitutional isomers because everything else is the same except for the connectivity. So that would be A, constitutional isomers. Okay, let's look at the next one here. All right, so what I see is a difference here. This bromine is on a wedge, but this bromine is on a dash. But then I also notice that I have another chiral carbon here. Okay, so in other words, this molecule has two chiral carbons, one here and one here, and similarly, one here and one here. Okay, so the bromine has flipped. In other words, the bromine has the mirror image in this molecule, but the hydroxy group remains on the wedge in both of those examples. So, so let's draw what I see here. Here, I see an identical relationship. Spatial, that's not how you spell spatial, is it? Oh well, identical spatial relationship. Now I could go and figure out the R and S, the absolute configuration for all four of these chiral carbons, and then I could compare those, but I don't need to because I can just do it visually. So this chiral carbon and this chiral carbon will have the same absolute configuration. I don't know if that's R or S, but I know it's going to be the same. Whereas this chiral carbon and this chiral carbon, they have switched absolute configuration. So for example, maybe this first one is R, maybe the second one is S. I don't know, but I know that they are different just because we have a mirror image relationship here. So I'll say different absolute configuration. Okay? Whereas in the yellow, it was the same. In fact, I'll write that instead. Same absolute configuration. Oops. Okay. So what do we have here? Well, they aren't identical because they aren't the same at both chiral points. They aren't enantiomers because they aren't the other absolute configuration at both chiral centers. And so they fall into that distereomer category where they are not superimposable and they're not identical. Okay? And they're not mirror images. So we know we can eliminate enantiomer and identical. So this would be, let's see, that would be a type of optical isomer D. Okay, because we know that optical isomers are enantiomers. I don't know how to spell these, so I'm just going to copy it. And distereomers. Okay. So specifically, these are distereomers. Okay. All right, let's look at the next one. So when I first looked at this, I got tricked on this one because I saw, oh yes, wedge, wedge, dash, dash. These are mirror images, which means that they're enantiomers, right? Well, I went too quickly and I didn't slow down to really examine the molecule. You want to make sure that when you're doing these questions, you're not rushing through them too quickly because you might miss a minor detail. The important detail in this case was to make sure that you knew where the hydroxy group and the bromine group were. Okay, so notice here the bromine's on the left and the hydroxy group's on the right, but the bromine over here is on the right and the hydroxy group is on the left. So I need to be more careful when I'm looking at these. Okay, so It's easier for me when all the groups line up and then I can examine, oh, is this on a wedge or is it on a dash? So what I'm going to do is I'm going to take one of these molecules and I'm going to flip them over, kind of like I'm opening the next page of a book, or I'm going backwards in the page of a book or something. So what I'm going to do is I'm going to take this molecule here, and since I have more room over here, I'll do it to this one. And I'm just going to flip it. You know, like I take a coin and I flip it on the other side. So what that means is my molecule, if I flip it over, is going to look like this. So if I just imagine flopping it, my OH, which was on a dash, will now be on a wedge. And same thing with my bromine. My bromine, which was on a dash, will now be on a wedge. And so now that I have this, now I'm going to use this because it looks a little bit more like this in terms of lining up the functional groups. I'm going to use this molecule to compare to my other isomer. So if I take this molecule and I imagine it coming over here, how does it line up against my first isomer, potentially, my first molecule? Well, let's see here. Oh, wow. That lines up perfectly. The wedges all match. The functional group connectivity all matches. So what that means is these two molecules are superimposable, okay? Which means they are identical. So let me put that over there. So it was a little bit hard to see with this molecule, but once I just manipulated it in space, comparing the two molecules is much easier, and I could quickly see that they're actually the same molecule. So they are identical, which is E. All right, and the last one here. Okay, so I have a bromine and an OH, and I have an OH and an OH. I don't even have a bromine on this molecule. So in fact, if I look at the molecular formulas here, 1, 2, 3, 4, 5, this has C5H11, O, and then a Br. But my molecule on the right here has a molecular formula of C5H12O2. So they don't even have the same molecular formula here, which means they aren't isomers of each other. So that'll be F. They are not even isomers. Different molecular formulas. All right, what is the relationship between the two molecules below? Here's the thing about Newman projections, and just kind of knowing this is good to know. Conformational isomers really kind of annoy me because, I mean, they're basically identical. They're identical molecules. All you've done is rotate around a sigma bond. But it's important to know that rotating around a sigma bond changes the position in space of groups. So it's, you know, it's not important, okay? But Newman projections are awesome for visualizing conformational isomers. They're awesome for visualizing the rotation around a single sigma bond. And so a lot of times when you are talking about conformational isomers, you might be looking at a Newman projection, okay? So that's just something good to know, because that's what a conformational isomer is. It's all about rotation around a single bond. So what's the relationship between the two molecules below? Well, first let's check to make sure that they are in fact isomers. So I've got the carbon in the back of the Newman projection, and I have the carbon in the front of the Newman projection. So that's 2 carbons, plus this carbon and this carbon, so that's 4 carbons, so C4. And if I count up all of my hydrogens, that's 6, 7, 8, 9. Let me make sure that's right. 6, 7, 8, 9. Yeah, that's right. Okay, so C4H9 and then Br. Yep, and then let's check this one. So I've got the front carbon and I have the back carbon that I can't see, plus these two, so that's C4H, so there's 6, 7, 8, and 9, so there's H9 and then a Br. So yes, they are in fact isomers, so that's good. Now let me check the connectivity. Okay, the connectivity is the same. So if I draw this the way that it looks, I have the front carbon and the back carbon of my Newman projection. And on the front carbon, I have a methyl group. And on the back carbon, I also have a methyl group. So I guess I'll draw it like that. And then also on the front carbon, I have this bromine. Okay, and then I have hydrogens. I'm not going to draw the hydrogens because they just make things look a little bit messier. So here, let's look at this Newman projection. Here's the front carbon, here is the back carbon. And on the front carbon, I have a methyl group and a bromine. Okay, a methyl group and a bromine. And on the back carbon, I have a methyl group. And so they both have the same groups. Oh, let me just draw that. So they both have the same groups with the same connectivity. So they are not constitutional isomers. So let's see, what else is the difference? Well, if everything's the same, the only other thing that we can really look at is where these groups on the Newman projection are. So here the methyl group is here in the bromine here, and there's a hydrogen there. Notice the front carbon on this Newman projection lines up exactly the same way. The methyl group on top, the hydrogen to the left, the bromine to the right. Okay, so really all we have to do is just look at the relationship of the front carbon to the back carbon. So here we have a methyl group, and it is 60 degrees away from that top methyl group. Here's this methyl group, and it is 180 degrees away from the top methyl group of the front carbon. So all that we've done here is we've taken this back carbon methyl group, and the hydrogens, right? And we've rotated them about 120 degrees to get them down into this position, which means all that we've done here is rotated around the sigma bond between the front carbon and the back carbon that we can't see. In other words, we've just rotated around that. So these are configurational isomers. Nope, I lied. See, this is why you got to get good at this. These are conformational isomers. Whew. Okay, you want to be careful because these two sound the same. Conformational isomer means you can change the conformation. Configurational isomer, I don't really know how you can remember that. That is when you're getting into geometric and optical isomers. Okay, so don't make that mistake. Be very careful between the two. They sound similar. Okay? All right, how many constitutional isomers of C3H7Br exist? Whew, okay, so constitutional isomers mean that they have different connectivity. We've got only 3 carbons, so there's only so many things we could probably do. And then we have 1 bromine. So if this is carbon A, this is carbon B, and this carbon is exactly the same as A, so we will call it carbon A. That means that there's only 2 different types of carbons here, A and carbon B, which means the bromine can either be on carbon A or it can be on carbon B. So I only have 2 possibilities for different connectivity. So I can have the bromine here, or I can have the bromine here, right? If I try to put the bromine here, what I've done is I've actually just drawn this twice. So you don't want to do that. That's why you want to identify how many unique types of carbons you have. In this case, we only had 2 unique types of carbons, A and B. So the answer for this is 2. All right, we are on our last question here. There are a few constitutional isomers of C6H12 that are both cyclic and have cis trans isomerism. Okay, that's interesting. How many carbons are in the largest possible ring that C6H12 can possess and still have cis trans isomerism? Now remember, cis trans isomerism can be one of 2 things. It can be referring to double bonds, so you have a cis double bond or a trans double bond, or it can be referring to a ring that has 2 substituents on it, where one's going up and one's going down, that would be trans, or both of them are going up, or both of them are going down, and that would be cis. So first of all, we have to have a ring, and we only have 6 carbons, okay? So if we have to have a ring, my first assumption is we're going to have the ring-related cis trans isomerism, okay? So I'm not going to be thinking about the double bonds first. I'm going to be looking at this in terms of a ring cis trans. So if I need at least 2 substituents, and all I have are carbons, then that means that my ring has to be 6 carbons, but I need to have 2 saved for substituents. So my largest ring can be 4 carbons. 1, 2, 3, 4. And that will leave me with 1 carbon to be a substituent and another carbon to be a substituent, okay? So in this case, I have the trans written, and in this case, I have a cis written. Okay, but I could have drawn it this way as well, and that would have been exactly the same molecule. So these molecules are the same. Okay, they're both cis, and if you flip it, they will look like each other. So the question was, how many carbons are in the largest possible ring that a carbon with a molecule with 6 carbons can possess and still have cis trans isomerism? Is 4, because we need to save at least 2 carbons for being substituents. That's it.